Okay, I just wanted to give you a few more examples on some conservation of angular momentum following a collision. And I noticed we didn't really have enough problems with inelastic collisions. So I thought, well, it'd be a good time to do some. So I've come up with two here, and you can see them, and they'll give you a little bit more practice in seeing what fits together. So first of all, let's take a look at this problem here. Got a bullet going sideways. It strikes a board that's sitting on frictionless ice and hits near the top end and is embedded. So it's embedded means we have a perfectly inelastic collision. And so in the end, I suppose if you calculated the kinetic energy compared to the initial kinetic energy, so initial is just the bullet and final is going to be the system, then we should see that there's some loss in energy. So I will leave that to you as an exercise, but it's something you should do just to make sure you can do it, right? And see that it decreases. So what's qualitative is what's going to happen here? Well, if we start, we've got, this is looking down. We have a bullet. There it is. It's 10 grams, and it's going 30 meters per second. There's the center of mass right there, halfway up the board. And it's, this is 1 kilogram. That's 1 meter. This hits a point here, or it's going to hit a point, 0.1 meter. So that leaves 0.4 meters down to the center. So this is the initial looking down, and the final looking down is going to be something like this. The bullet's going to be embedded in here, and since it's on frictionless ice, it's going to be rotating about the center of mass this way. If it hits on the top, it's going to go that way, right? And the center of mass is going to be moving this way, right? Since there's only momentum in this direction to begin with an x, we don't expect any y momentum. It's going to stay in x. And so the board will be sliding this way as it rotates around. That's what we expect to happen in the final case. So we'll do 2 parts here, and we'll start with the rotation. I'll get that part first. There'll be an omega final right there, and then there'll be a v final of the center of mass that we'll get later on. Again, it has to rotate about the center of mass because there's no other forces here. There's nothing tying a particular axle, and so if there isn't, just like when we threw those frisbees that were weighted, it's going to rotate about the center of mass. So the key thing in rotation is angular momentum is conserved. Total angular momentum is conserved. And so that means L bullet initial plus L board initial is equal to L both final. Now remember that for a point object, we had a choice of using mr squared for I and omega, or we could use the mv times r sine phi. And it turns out we want to use mv times r sine phi here because that's more convenient. Because if we look, this distance here, well, even if we're out here, what is r sine phi? Well, if this is r and this is phi, this distance right here is r sine phi. And it's constant, right? If we're over here, then distance r will be there, and that's still r sine phi, because r is still a hypotenuse, might be different. So is phi, r sine phi is this distance, we're right up over here, then phi is 90 degrees, so r sine phi is just this distance. So it doesn't matter what it is, r sine phi is always going to be that distance to closest approach. And so r sine phi right here is just going to be the closest distance, which in this case is equal to the 0.5 minus 0.1 is equal to 0.4 meters. That's r sine phi. The minus, we need a minus sign in front of here, and the minus sign comes from the fact that it's going clockwise about this axis, right? Here's the axis, that's going that way. That's a clockwise rotation about the board's center mass. And so let's continue along here. And what's the mass here we know, and v we know, so this part we can get. What's the board momentum? That's not moving for the initial, and so that's equal to 0. And so this plus 0 is equal to that, and this is I final omega final. Now we have to figure out what I is. I final is equal to I board plus I bullet, which is equal to 1/12 ml squared plus m d squared. So this here is about the center mass of the board. Now you might argue that, well, when we put the bullet in here, moving the center mass ever so little bit away from that, that's a really, really small effect because the mass of the bullet is so small compared to the mass of the board. We're going to neglect that because it would really wash out in the number of significant digits we keep. But if we can, if we do take that, this is 1/12, 1 kilogram, 1 squared meters squared plus 0.01 kilogram times 0.4 squared, and that's 0.083 plus 0.0016. You see, even this has a almost tiny effect. It's going to change the 8.3 into an 8.5. And so it's a couple of percent effect for this. The amount you get by changing the center mass is smaller still. And so this is 0.085 kilogram meter squareds. Okay, and so if we then draw everything down here, this side here is minus 10 gram is 0.01 kilogram, V 30 meters per second, R sine phi 0.4 meters. Multiply that out and you get minus 0.12 kilogram meters squareds per second. And let's drag both of these down. And we end up with minus 0.12 kilogram meters squareds per second is equal to 0.085 kilogram meters squareds times omega final. Divide both sides by that. Omega final is equal to minus 1.4 radians per second. Or if I convert it to a frequency of the final is equal to minus 0.22 hertz. The minus here again means it's clockwise. And 0.22 hertz is like 5 seconds to go around. So it's not going around very quickly. Well, between 4 and 5, right? If it's 0.25, it'd be 4 seconds to go around. It's 0.20, it'd be 5, somewhere in between 4 and 5 second period. Okay, that is the rotation. Now let's get this linear velocity here. First, it's only an x, and we have the mass of the bullet, velocity of the bullet, plus the mass of the rod, velocity of the rod is the board, is equal to, they tied together, so we add their masses, v final. Plug in the numbers, 0.01 kilogram times 30. Plus 0 is equal to 1.01 kilogram times the final, and you divide both sides, but this 30 times that is 0.3, so the final is equal to 0.3 meters per second, and that's in the plus x direction. So it's moving slowly. Because the bullet doesn't weigh that much compared to the board, it doesn't make a big difference. It's slowly moving along and slowly spinning around as it goes. Okay, that's a reasonably complicated problem, but it really should show you how you go through these things step by step. The big thing is this. We hadn't done an example. One of the reasons why I did the extras, we hadn't done an example where we used this point object formula. I showed it to you, I talked about it, we hadn't used it. So here we used it, and you see how it comes in. And so we're combining the point stuff with the bullet, and of course we can't, when you get both together, we can't use point stuff anymore because we have this around. So we're forced with the I omega on the final case, and we get this. Now, what happens if we have something here that's not 0 to begin with? Well, let's do another example. Okay, we have a, in this case, 100 gram 10 centimeters plate spinning around at 78 RPM. So an old record player, if you want, on a vertical axis. So it's in a horizontal plane. So there's something spinning around the plane. I take and I drop some, what did I drop? Chunk of gum. I drop something of gum down, it lands on it, it sticks. And now, what's the final rotation speed of the disc plus the gum, right? So initially I have a disc and it's rotating around, and I have a chunk of gum and it falls straight down on it. That's initial. And the final case, I have the disc with a chunk of gum on it, and it's rotating probably a little bit slower, right? So we start with L initial equal L final, and this is about a vertical axis. Now, L initial, well, L gum initial is equal to 0 about the vertical axis, my C, yeah, over, about a vertical axis, because it's L is about a horizontal. Since they're perpendicular, it doesn't really do much. It just comes down and goes plunk. So going straight down onto this disk, it doesn't change how the disk is going to rotate or not. It's as if it wasn't there. It'll go plunk, it'll stop. The frictionless, should say it spins frictionlessly here. Okay, once there's a frictionless spin, so it doesn't matter, there's a force that stops it. The L disk initial is equal to I omega initial, and I is equal to 1/2 mr squared, which is equal to 1/2 times 0.1 kilograms times 0.1 meters squared, which is 5 times 10 to the minus 4 kilogram meters squareds. And omega initial is equal to 78 revolutions per minute. And you've got 1 minute is 60 seconds. And you've got 2 pi radians per revolution. And you multiply that, so it's 8.17 radians per second. So those quantities, so that means that this initial, you bring them all in, is multiply them out, it's 4.1 e minus 3 kilogram meters squared per second. Okay, I final is equal to I final disk plus I final gum, which is equal to 1/2 mr squared, which is the same as it was before, plus mr squared. Right, this is as it was before. This is equal to r since it hits the edge. It's the same radius. And so if you multiply these two out, you get 6e minus 4. Again, it's kilogram meters squared. And so we jump back now to the L initial is equal to L final. L initial is 0 plus 4.1 e minus 3 kilogram meters squared per second is equal to 6e minus 4 kilogram meters squared times omega final. And you divide both sides by that, and you get omega final is equal to 6.8 radians per second. It was 8.17, now it's 6.8. It's slowed down. If I convert it backwards the way I did here, I find it 65 revolutions per minute, RPM. And so that is another problem where you have something that is moving, but since it's moving sort of the wrong way to give us any rotation, it doesn't contribute, and we just get a 0 for that piece, but it does contribute to the moment of inertia in the final case, and that gives us our reduction in the final rotation speed because the moment of inertia is increased, right? Moment of inertia goes up, which is essentially what's happening here, right? We've got a disk with a moment of inertia, now we've added increased moment of inertia without really adding any more energy to the rotation, so the rotation speed has to decrease because we haven't had any momentum because it's going straight down. No momentum about this axis, no torque. And so we have a decrease in the rotation speed. Now, if this sticks, then you have to probably figure, okay, probably lost some energy. If we calculate the initial energy and the final energy here, which of course are half I omega squared, that omega squared drops. I increases just barely from 5 to 6. This changes by more, especially when you square it. And so yes, you're going to have lost energy. Just like in here, I forgot to say at the end, we said at the beginning, the energy here, the kinetic energy, potential is 0, right? Potential energy is equal to 0 always. The kinetic energy is 1/2 m v squared plus 1/2 I omega squared. And if you calculate the initial and the final, right, initial, it's just the bullet's linear velocity, half mv squared. In the final case, you have the masses together with some velocity, and you have this I that we calculated over here, some I final, with the mega final right here. And so you can actually go in here and take this and some of the masses and that, put them in for the final. The initial has just that piece. Work it out. You'll see that energy is lost. And if you don't, well, maybe you need a little bit more practice. And that practice is the end of our practice. And so that's the end of our little talk here. See you next time.